Here's a picture of a hyperbola. It's got a focus over here, and a directrix over here, and it's got some eccentricity. Maybe it's around 2, maybe a little bit less. But there is an eccentricity. And when you have a hyperbola and a focus and a directrix, if I call this point P, and I call this F, and I call this point D, it will be a fact that PF will equal E times PD. Now, this, if I just had the hyperbola with no focus and directrix drawn in, this could be the focus and directrix, or maybe the focus and directrix is underneath. It would be the same 2 branches of the hyperbola regardless. So I'm going to call this F1 and D1, and I'll call this F2, and I'll call this point over here D2. Because if those are the focus and directrix, then from this point P here, it would be true that this would be equal to eccentricity times this for the other directrix. So I'm going to put a 1 here and here, and put underneath it, actually I'm going to put above it, PF2 is the eccentricity times PD2. Now if I subtract these 2 equations, I get PF2 minus PF1 is equal to EPD2 minus EPD1. I can factor out the E minus PD1. But see, PD2 is this long line, and PD1 is this shorter line. And when we subtract them, we get this yellow line. So I'm going to say that equals E times D1, D2. Just a line segment. And even if P was over here, let's say, this same thing would happen, where the difference between these 2 distances would be E times, this one would be E times that. And if I was using this other one, it would be this length. This times, it would be E times that. Either way, when I subtract them, I would get the same thing in the middle. So D1, D2 is a constant. And I'm actually going to add a new variable here, which if I throw in the center of this entire hyperbola, and I'm going to call this little distance from the center to the directrix lowercase d, so that will be lowercase d also, and I'll say that equals 2 lowercase d. Now if it's true that for any point PF2 minus PF1 is going to be a constant, which is what we just showed, it's also that constant. What is that constant? Well, that constant is going to be true for every point, so it's also going to be true for this point, which I'll call V. So the constant is going to be also VF2 minus VF1. But VF1 is also equal to this thing over here. Why don't I just call it, I'll call this V1, F1. And I'll call this guy V2. So these blue things are equal to each other. So like a symmetric thing going on here. And what I'm left with when I subtract the red minus the blue, but take the blue off on this side, I'm left with this green thing in the middle, which is going to be 2a. So the magic number is always the distance between the 2 vertices. Now we saw from the last page that the magic number was also 2d over here. So I can also throw in that equals e times 2d. I notice over here I accidentally left the e off of that. And I get a new relationship then that 2a is equal to e2d, or a, if I divide both sides or actually E equals, if I divide both sides by 2D, I get A over D. That might come in handy in a second. Now I want to do a proof of something that I said in an earlier video, that eccentricity always equals C over A. Using this picture with the directrix, I want to show that this E is the same E as when I do the thing with the focus and directrix. So here come some variables. C is the distance from the center to the focus. A is the distance from the center to the vertex. That makes this little piece over here C minus A. The distance from the center to the directrix I'll call D, and that makes this little piece here A minus D. Now this piece here can also, besides being equal to C minus A, there's another way to look at it, because the distance from the focus to any point on the hyperbola is equal to E times the distance from that same point to the directrix, which in this case is A minus D. So I have this fact. I can look at this line segment here, this one, as C minus A, or as E times A minus D. And I can replace the D. If I come back over here and rearrange it, I could write it as D equals A over E. So if I come back here, A over E, and I get C minus A equals EA minus E times E cancels, becomes A. Add A to both sides, C equals EA. Divide both sides by A and get E equals C over A, which is what I was trying to prove. So the eccentricity from the focus directrix definition is the same eccentricity as C over A from earlier video. Two more mysteries. One is this B value here. You know, we used it to make the graph. We went right 5 and left 5. Then we went up 3 and down 3, but those points weren't actually part of the hyperbola. They just helped us draw the box, and then we drew our hyperbola. But why is that? Why are the asymptotes, in this case, why are the slope of the asymptotes B over A, or in this case it's 3 over 5? I want to show you why that is. If we take this equation and rewrite it as y equals, well, to do that, I would start by subtracting 1 from both sides and adding y squared over 9 to both sides, then multiplying both sides by 9. That's x squared minus 9 equals y squared. Then I would take the square root of both sides and get plus or minus the square root of 9 over 25 x squared minus 9. Now, when you make x big enough, this 9 won't really matter anymore because it's so small compared to a really large x. So I get plus or minus 9 over 25x squared, which becomes plus or minus 3 over 5x. And the 3 is b, and the 5 is a, and that's how that works. That's why this box method works for graphing it. And the final mystery is why, for a hyperbola, does c squared equals a squared plus b squared? Well, in an ellipse that wasn't true. For ellipse, the relationship was c squared, or was a squared, equals b squared plus c squared. But for the ellipse, there was a really easy reason why. If this is b, this is c, and this is a, because the magic number for an ellipse, the sum to any two foci, is 2a, if I were to draw two lines like this to make equal isosceles triangle, they would add up to 2a, so individually each one would be a, and we'd have this nice right triangle with the relationship a, b, and c are in it. A squared equals b squared plus c squared. For a hyperbola, For a hyperbola, it's not quite the same. Hold on a second. See, in this picture we have, this would be A, this would be C, and B is sort of this kind of the top of the box. So there's not really a nice right triangle to create here. Well, through a lot of research I found a diagram where there is a right triangle that has A, B, and C in it, and I'm going to show you that. Okay, now here's the diagram. It's definitely an intimidating looking diagram, but let's just see some of the pieces here. For one thing, from here to here, OF1 is going to be C because it's from the center to the focus. Some more things I could identify. This is the top of the box, so this here is B. And over here, I'll put my A up here, although there's A's in other places also. So there's A, B, and C. Now, how do I get them all into one triangle? Well, that is pretty tricky, but here it comes. I have this point P, which is it's actually not there. It's actually at the end, if you can imagine that, of the branch of the hyperbola. Now, the further away P is, the more parallel F2P and F1P. If P is kind of closer, like if P was over here, F2P and F1P would definitely not be parallel lines. But the further away P is, the more parallel they get. And P is so far away that we're actually going to go ahead and say that those things are parallel. And here I have this line from F1. This line is drawn so that it's perpendicular to the asymptote. That's why I have a right angle here. Now, if these lines really are parallel, then this will be a right angle also, even though it doesn't quite look like one. Okay. Another thing is that for any points on the hyperbola, PF2 minus PF1 equals a constant, which is 2a. Now, though these lines don't look, these lines don't look like they're parallel, but imagine if they were, and if this one was like a little bit bigger than this one, that difference would be 2a. In other words, this DF2 is equal to 2a. And while we're at it, this F2, F1 is equal to 2c. Now, I see two triangles here. There's this one and this one. And they are similar triangles. They both have right angles in them, and they actually both share this angle here. So those are similar triangles. So they're in proportion. And the proportion is 2 to 1, because if this is 2c and this is regular c, and this is 2a, this here will be regular a. So I have a right triangle here with a in it and c in it. And I have another right triangle up here. It has A as its top side and B as its sort of vertical side. And what I want to show you is that these two triangles, this one here, I'll just make it fully green, and this triangle here that I'm going to make red, they are congruent triangles. They both have right angles in them. They both have side A in them. This one, this red triangle has side A over here, and this green one has side A up here. And it's not so obvious, but these triangles have another angle that's equal, namely because of alternate interior angles. Those two angles are equal. So these are congruent triangles, which means that this side here, even though it doesn't quite look like it, must equal B also. So I have this little triangle here, which has, I'll just draw it. That's this triangle right here. Has C, A, and B in it, and it's a right triangle, and C is the hypotenuse, so C squared equals A squared plus B squared.